The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thank you for attending today's webinar. Today we'll be building a FaultTree from a schematic. Joe, can you see my screen?
Not yet.
Okay. Now?
Yep, just came up.
Okay. So this was the schematic I sent to everyone in a. This is a schematic that was actually in the invitation. Later in the meeting, after we've demonstrated the FaultTree, I'll be posting a copy of the completed FaultTree, which you can find in handouts. My name is Jeremy Heenek. I do business development here at Isograph in North America. And I also have Joe Belland on the line with us. Joe does our technical support and training here in North America. Or I guess he heads it up, I should say. So this webinar, building a FaultTree from a schematic. So we have a lot of webinars on related topics. So here's a list of some of the webinars we've done this year. The only one that would be not on this topic would be the availability workbench. I thought I would just include it in case anybody's interested in optimization, Monte Carlo simulation. You can view all of our past webinars on our website, on the blog section. I've posted recordings of each of these meetings as well as several other on different topics and presentations. Just a few things before we get started. You'll see on your screen there's a pop-out on the right-hand side of the screen. You can minimize that pop-out by clicking on this arrow here in the top left of the pop-out. And during the meeting, there's too many people in this meeting for me to address it raising of hands. So please don't raise your hand if you have questions. Please use the questions dialog. So everybody's muted, again, because we have too many people in the meeting to have kind of open audio. If you have any questions, please post them in the questions dialog. I'll be answering questions during the meeting. And when questions that come up that might be of interest to everybody, I'll ask those to Joe once in a while when he pauses throughout the meeting. Otherwise, Joe, if you're ready, let's get to work on this. You ready?
Okay. Yeah.
Yeah, I'm making you the presenter right now. You got that?
Yeah. Let me just share my screen here. Can you see my screen, Jeremy?
Yeah, I can see it.
Okay. This is in some ways a sequel to a webinar we had done a number of months ago about building a schematic in the FaultTree. We've done another system. This time we're going to take another system and sort of use it as an introduction to the FaultTree. Some of the shortcuts and tips and tricks you can use while converting a schematic into a FaultTree. This one, I think the schematic's a little trickier and the system may be a little more complex. So it'll serve as a better example, I think. So Jeremy sent out this description, or this schematic of a rocket propulsion, well, really a monopropellant propulsion system that would be used in a spacecraft. The first email he sent didn't include a description. I think he sent it out later, so if you saw that, then sort of know what we're going over. But I'll give a quick rundown of the way this system works. This is a monopropellant system, which is a monopropellant system in a spacecraft is not generally used for launching or any sort of serious thrust. It's mainly used for control and maybe altering the orbit of a satellite or of a spacecraft. You can use it to make fine adjustments and fine controls to the spacecraft's velocity and direction. The way the monopropellant rocket propulsion system works is we store inert gas in this pressurization tank up at the top. What that inert gas does is when we open up these isolation valves, it will push on our propellant tank. The propellant is stored on one side of the bladder, and there's space on the opposite side for the inert gas to force the propellant out, so that bladder can change in shape to push allow the inert gas to push the propellant out through a thruster isolation valve, the thrust chamber inlet valve into the rocket engine. The propellant used in this example is hydrogen peroxide, the chemical formula of H2O2. It's useful because you don't require an oxidizer. It's just when it passes over the catalyst, that breaks down the hydrogen peroxide into its component hydrogen and oxygen, and that breakdown releases energy, and that's where you get your thrust from. So it's useful if you don't have to carry an extra oxidizer, and it's an efficient reaction, although it doesn't provide as much thrust as other oxidized chemical reactions. Along the way, we have various safety systems, relief valves, if there's ever an overpressurization event, and various control valves to make sure we don't force too much inert gas or too much propellant to overload the system or overpressure it. In addition to the mechanical components that are actually involved in the firing of the system, the schematic also shows the electronic components that manage the system, that manage the firing. So we have 3 circuits. The arming circuits is this top one here, the firing circuits down here, and the timer circuits right here. The way they work is when you want to arm the system, you depress switch S1. If this is a manned spacecraft, the pilot would probably manually depress it. Otherwise, the computer system depresses switch S1, and that will complete a circuit on our arming circuit, which will signal which will cause the inert gas isolation valve, IV1, and the thruster isolation valve, IV2, to open. That allows the inert gas to flow into the bladder and start pushing the monopropellants towards the thrust chamber inlet valve. But at this time, IV3 remains closed, so the rocket will not yet fire. When we want to fire the system, we depress switch S2. That will complete the circuit here. Oh, by the way, that's another thing that S1 does, is it closes relay K3, which allows the arming circuit to be completed with the depressive S2. Relay K2 is a safety feature. When you depress S1, relay K2 temporarily opens the arming circuit, so you can't accidentally fire the thruster when you're trying to arm it. It's just a little safety mechanism. Depressing S2 will close the firing circuits and signal relay K5 to close the timing circuit. And that will open the thrust inlet chamber valve, IV3, finally allowing all the monopropellants to flow into the thrust chamber. The hydrogen peroxide flows into the catalyst, breaking it down, causing the thrust, the chemical reaction which provides thrust. The timer relay, K6, is pre-programmed with a fixed, or with a set time for how long do we want this propulsion to last. It's pre-programmed. We need to thrust for 10 seconds or for 30 seconds, however long we need to, it's been pre-calculated for how long we need to adjust our course. When the timer relay times out after the end of the thrust, it will momentarily open. That breaks the circuit in the arming circuit, which will close valves IV2 and IV1. K3 will also be de-energized and it will open, closing the firing circuit, which will in turn open the firing circuit, open the timing circuit, and open valve IV3, and restoring the thruster to the dormant state where everything's closed off. All the valves are closed. Okay. So that's the description of the system. And we want to build, what we've done here is we've defined the system bounds that we're going to consider when we're doing our reliability analyses on the system. Obviously, this is a critical system. If we're doing a fault tree analysis on the spacecraft, or we're performing a reliability analysis on the spacecraft, that would be something we want to consider during the design stage to prove or verify that our system is reliable and suitable for use in a spacecraft. So we've defined our system as those items shown in the schematic, and we've included both mechanical and electrical items that are going to be included. Now, once we've defined that system, there's a few different top events which present themselves, different reliability or system failures which could impact the system. Three ones that jump out at us would be a failure to provide a propulsion on demand, meaning you push the button to fire the thruster, but no thrust comes out. That could be a problem because if we need to adjust our course, would inhibit our ability to do that. A second one would be an inadvertent firing of the system when not required, meaning we're just sort of happily floating along through space in our happy little orbit, and then all of a sudden the thruster goes off and veers the spacecraft off course. That obviously also would provide a problem. The third possibility would be that the system continues to fire after it has been commanded off, meaning we've pre-programmed our course adjustments, we fire up the system, and then when it's supposed to shut off, it keeps on firing. And that would throw us off course as well, because these are all very carefully calculated courses. So for this example, we'll be examining that third possibility, the continued firing of the system after it has been commanded off. Okay, as I build through this fault tree, there's a couple of things that we can keep in the back of our head, and you'll see as I go through, things that will help us visualize the fault tree. Sort of the point of this web demo is I want to help you go from this complicated schematic, it's a rather complicated system, and it might not be immediately clear how to go from that schematic to a fault tree. So this web demo is going to help us sort of break it down, do our little piecewise investigation, deductive root cause analysis into the system. One of the excuse me, one of the rules we can keep in mind that helps this breakdown is to consider whenever we're looking at a specific failure, we ask ourselves, is this a system event or a component event? A system event is a failure that's directly associated with a single component, and a component event is not. It's directly associated with, or excuse me, I have that backwards. A system event is not directly associated with a single component, meaning there's multiple different failures combining. And a component event is directly associated with a given component. And the handy thing about that, why we keep this in mind, is component events are very, I guess you might say, formulaic. You can, if you say this is a component event, that sort of tells you the structure of the fault tree, what it's going to look like. A typical component event will look like this. We have a top gate, or excuse me, not necessarily a top gate, the component event gate, which will be caused by two failures. The primary fault of the component, that's the component fails to perform its function due to its own internal failure, and the command fault. The command fault is when the component does not receive the whatever it needs in order to perform its function. That could be electricity if it's an electrical component. It could be a command if something further up the chain tells it what to do. It's not receiving that required command. So we keep this in mind because it can help us as we're building backwards through the fault tree. Okay. So to begin with, we have the schematic, and we're going to identify the immediate causes of the event. Why would the thruster continue to fire when it's not supposed to fire? Well, what would happen in order for that to happen is the valves have to remain open, right? We have to, if the valves close, if any of the valves close really, the thruster stops. But if the valves remain open, then the thruster will continue. So that's where we're going to start. In particular, we're going to focus on IV2 and IV3. If IV1 closes, it's true that the inert gas will stop, but there will still be enough residual pressure in the, remember we've got a vacuum of space out here, and we have monopropellant in here, so there's going to be a pressure differential. So even if IV1 is shut, there's enough residual propellant, residual pressure in the monopropellant tank sort of suction the monopropellant out, and there will be continued, it won't be a full thrust, but it will be enough thrust to negatively affect the course of the spacecraft. So in order for the system to fail, both IV2 and IV3 remain open. The shutdown of either of those or the closing of either of those will stop the monopropellant flow and cut off thrust. So that's where we're going to start. Now I'm going to jump into the reliability workbench and start building this fault tree as we go. The top event, adding our top events and the immediate causes of that top event. So I'm not sure if you can see that, but you can see I have quite a few windows open. Here's my reliability workbench window. I'm starting with a new blank project. I'll point out some of the shortcuts I'm taking along the way. The first shortcut I'm going to take is what I did is I predefined all the components within the system. So if we go to that PDF, that fault tree, this example comes from this PDF file. This is a NASA document, FaultTree Handbook of Aerospace Applications. It's actually freely available if you search the web for that title, FaultTree Handbook of Aerospace Applications. It's typically the first hit, and it will take you to this website where you can download it. Anyway, on page, I think it was 140 of the document has that schematic. And on the next page, it has a list of all of the components within that schematic. So what I did is I predefined that list of components in Microsoft Excel. So here's a list of all of the components that I could potentially need. So this is one way where we can save ourselves from some effort. I can start with this list and then just import them into the Reliability Workbench. That way I don't have to be creating them as I go. I can just have all that information ready to go and drop it into the fault tree as I get to the relevant events. So to import this, I'm just going to select all this data here in Excel. Control-C to copy to the clipboard, or click the copy button. Now I jump back to my Reliability Workbench window, and I'm going to go through the import wizard. File, import. I'm importing from the clipboard, so I'll tell Reliability Workbench that, and that the column names are in the first row. The very first row of my file is the name of the column. The data I'm importing, so I'll go to the Table Matches tab. That data from my clipboard, I want to bring that into the primary events table. Primary events table is a list of all of the events in your fault tree project. The next thing is the column matches. I need to tell it which columns in the events table the data matches to. I was careful to call them ID and description in my Excel file. That matches with the names in Reliability Workbench. So I use the auto match button. And the program automatically detects which columns they should fit into by their names. And then I click the import button. Runs through, import complete. I click OK. This is the type of import that I'm going to do frequently. I might save the settings in the template so I don't have to reset all those options each time. I think this is going to be a one-off import, so I don't need to do that. You can now see on the left-hand side of Reliability Workbench, I now have all my events imported, so they're all ready to go. All my basic events, I can just drop into the fault tree as I build. The next thing I'm going to do to save myself some time is you'll notice my view on the right-hand side. You're probably used to viewing just the fault tree diagram on the right-hand side. That's the way most of the time we do it. My favorite view, actually, for building a fault tree is the diagram and grid right window view mode option. That shows me my fault tree diagram at the top and a grid view at the bottom where I can view table information. A lot of the information in a fault tree is easier to edit or easier to change from a table view. It kind of gives you like an Excel-like spreadsheet grid. It's easier to navigate and type in rather than working through program dialogues. So that's a little shortcut I'm going to be using. I've set up the diagram and grid, and I've told it to show me the gates table. Yeah, and I'll be changing that, which grid view I'm showing as I go through building the system. I'm going to change the grid view to general view. Okay, so let's start building this fault tree. Excuse me. As I mentioned, I'm going to start by adding the top gate, the top event, the hazard we're interested in. Just like here, I can see the top gate down here. Rather than having to double click on it to edit it, I can type in an ID and a description from down here. This is why I have the grid view displayed. The ID and description I'm going to use, because our top event was a thrust continues after cutoff. So I'll call my top gate thrust continues. The description will be thrusters supplied with propellants after thrust cutoff. I'm not going to spell check my propellant, so the software can do that for me, so I'm just doing it as quickly as I can. So you'll notice as I enter it in the grid, it also appears at the top gate in the diagram at the top. Okay, so what were the immediate causes of that? Jumping back to my PowerPoint, here's my slideshow. So remember, IV2 and IV3 were the immediate causes of that. Thrusting continues. Isolation valve 2 remains open and isolation valve 3 remains open. So I'm going to add a couple new gates to represent those. So add 2 new gates. And again, I'll name them down here. This will be the IV3 open. Isolation valve IV3 remains open. This other one will be the IV2. So we'll rename that IV2 open. Isolation valve IV2 remains open. Okay, if you're wondering how I did a little shortcut there, you might not have caught it. With the field highlighted, I went back into edit mode. This is actually not a shortcut key unique to Reliability Workbench. Most spreadsheet or table applications use this, for instance, Microsoft Excel. If you press the F2 button on your keyboard, it will go to cell edit mode. So you can edit an existing cell, and pressing enter will finalize the edit. Okay, so let's start by breaking down that isolation valve IV3 remains open. I'm going to scroll my tree around. By the way, I don't know if you know this, but in Reliability Workbench 13.0.1, we now added the ability to use the scroll wheel, the mouse scroll wheel, to zoom in and out and scroll up and down on your diagram. So I can scroll up and down. You can't see what I'm doing, but I'm just rolling the mouse wheel on my mouse to do that. Along with that, and this is the change I think was cool, if you're using a touch screen, like a tablet, like I am, I'm actually running this from a Microsoft Surface Pro tablet, touch screens count as a scroll wheel. So I can actually scroll around now by simply touching on my screen with my fingers and sliding around. So I think that's just kind of cool. That's a little aside, but I think that's a cool new feature in Reliability Workbench 13.0.1. Okay, so let's continue on. So the isolation valve IV3 remains open. So that is a component event, as I talked about before. Component events always have a given format. There's the primary fault of the component and the command fault, which is it fails to receive the input it needs. So the primary fault is the failure of isolation valve IV3. Now I created that basic event already on the left-hand side. I can just click and drag to put it into the fault tree. There's isolation valve IV3. Now, I might want to do this, and I might, for this purposes, I'm not going to do it just for saving time. But in reality, we're looking at a particular failure mode of the isolation valve. So I might want to re-describe this instead of just isolation valve 3 fails or something like that. I'd want to say isolation valve 3 remains open. There's a specific failure mode I'm after here. For the purposes of our web demo, I will leave it as is. Okay, and then the command fault, there's going to be a new gate underneath here. The command fault is the electromotive force continues to be supplied with IV3 after cutoff. In other words, it's being commanded to stay open. That's the command fault. It's supposed to close, but for some reason, it's still commanded open. So let me change that. So this is the, I'll call this gate IV3 power. It receives power. Power supplied to IV3 after cutoff. Okay. Let's continue on there. So we're going to, right now we're looking at the IV3. So we're going to say, why does it continue to receive power? Why does the command fault continue? Well, the circuit would still have to be closed, which means relay K5, for some reason, has not opened. Okay. So let's go back into the fault tree. The command fault of IV3 would then have to do with relay K5. It's a component event because relay K5 is specifically involved with that failure. So the primary fault of it would be the firing relay K5 continues or remains shut, or the firing relay K5 failure to close, or excuse me, failure to open. Firing relay K5 remains closed or fails to open, however you want to describe it. The command fault of relay K5 would be the other possibility. So I'm going to add a new gate for the command fault. So that will be K5 power. Power supplied to K5 after cutoff. Okay. Continuing back, why would relay K5 continue to receive power? Okay, backing up the way, the arming circuit would have to remain closed, which would be because K3 has not opened, and relay K3 has not opened in the firing circuit. You might see a couple other places it can open, like K2 could also open, or a break in K4 here could also open. But keep in mind, those aren't supposed to open to shut it off. They could if they failed. You could have an arbitrary failure of K2 that opens it. But one of the rules in the fault tree, if you read that little math handbook, one of the rules that they give, which I think is a good rule, is no miracles. For instance, if K2 just happened to fail and open when it's not supposed to, right when the cutoff is supposed to occur, you'd be saved, right? Even if everything else failed, if K2 fails at just the right moment, that will open your firing relay and close it. But we consider that a miracle. We're not looking at or considering the possibility that K2 fails and saves our bacon. So we have that no miracles rule. So we're only looking at components whose failures could cause a fault rather than a component whose failure could save the system. Okay, that's just a little bit far-fetched. Okay, so K3 is our fault here. So continuing down, power supplied to K5 after cutoff. That would be the K3 arming relay has failed with its command fault. Electromotive force, so power is continued supplied to K3. Power supplied to K3 after cutoff. Okay, working our way back, still going down the list. Why does K3 continue to receive power? Will be the arming circuit would have to remain closed, which means there's two shutoffs, by the way. There's the timer relay, and there's also switch S3, which is sort of a manual shutoff. It can be activated by the computer system or by the pilot when the timer relay, if the timer relay doesn't shut off, we know the S3 can also shut the system. So both of those would have to remain shut in order for the arming circuit to remain closed and K3 to continue to receive power. So this is a system fault, not a component event. It's a system fault. So I'm going to add the gate or add two gates because there's two system faults. So gate GT1 will be the S3, the emergency cutoff switch. It remains open. Or excuse me, remains closed. It fails to open, okay. So I should rename this, it should be called S3 closed, right? S3 remains closed after cutoff. And the other one was the timer relay, K6 closed. Sorry about my typos there. K3 remains closed after cutoff. Okay, now each one of these is a command fault, or excuse me, is a component event. So there's two failure modes we could consider. One is the physical failure of the device, and the other is the command fault. For the switch S3, the command fault would just be it's not depressed. So either the pilot or the computer fails to shut it off. So we drag in the S3 event. That's the primary failure. The emergency cutoff switch fails closed. And the other events, I'm going to add any basic events in this case. The other possibility is the operational failure, the command fault. So whatever is supposed to command it open doesn't. So the pilot doesn't or the computer doesn't. Creating that as a basic event, because this is as far back as we're taking our fault tree. There's no further depth in the schematic to drill down into. So let me rename that. I'm not going to rename it yet. I'm going to put that in just a minute. Because I want to do the same thing for K6. So I can drag across the primary failure of K6, the timing relay. Primary failure is for it's open. The command fault is the timer. If its timer doesn't open, then we'll also have an error. So there's two failure modes of relay K6 we need to consider. One is the actual physical opening mechanism of the relay. The other is the timer mechanism of the relay. Okay, so to rename those two events, I'm going to change my grid view to primary events. Now I can name them here. So EV1 is going to be my S3. Keep it. S3 operational failure, right? Command fault. The operation of the command is not applied to open it. So operational failure to close. That's S3 to be commanded open. The other one for the relay, the K6 timer, was primary failure, the timer to time out. Okay, there we go. So we've built this branch all the way down to the basic events, as you can see. So now we need to look at the relay valve, or excuse me, the isolation valve IV2. That's the next part of the fault tree, is to build this leg IV2. So continuing down, the immediate causes of that would be the arming circuit remains open, or the arming circuit remains closed, causing the isolation valve 2 to remain open. The two components responsible for opening the arming circuit, again, are those same switches S3, the timer relay K6. Again, actually I'm getting a little bit ahead of myself. I need to consider the component events of IV2. So that the primary fault of the component, IV2 remains open, its mechanism fails to shut, and the command fault, which is the arming circuit. So let's start with the, let me see where I'm at. Let's start with the primary fault. Here's isolation valve IV2. It fails to close. And then I'll add a new gate. Jump back to my gates table so I can name that. This is IV2 power. Power applied to IV2 after cutoff. That's the command fault. Now our command fault for that, I'm going to go back to the slideshow, or just to the schematic. The command fault again is those same two switches, S3 and switch S3 and timer relay K6. Those are the same failure modes we had for IV3. So rather than having to re-enter that information, I can copy and paste or duplicate it. So it's these two events here. Okay. Two different ways I can reuse them up at the top here. One would be copy and paste. The other one, I'm just going to show this because this is a shortcut many users might not know about. There's a shortcut to reuse existing gates or events. And to do that, you click the Add Gate or Add Event toolbar button. And instead of left-clicking to add in a new item, I can right-click to add an existing item. So S3 closed and K6 closed are the two items I want to add here. So I'm going to right-click on this gate. Reliability Workbench will open a dialog with a list of all of the gates within my project. So I just choose the ones I want. K3 remains closed after cutoff. Add it in. And again, the same thing, K3, power supply, or excuse me, K6 closed. K6 remains closed after cutoff. And it looks like I put the wrong description there. Yeah, I can fix that description from down here. There we go. Okay, so I added in those two gates here. They're linked gates, you'll note. They're linked down to these, you see the transfer out and transfer in symbols. The little line underneath it means that it's connected to somewhere else on the same page. So it's the same thing that appears in two different places. Reliability Workbench won't waste screen space or, by drawing the same thing twice. You can see that when you get to that gate, you just find the other, where it continues on the page. Okay, so that's the completed structure for this fault tree. Jeremy, shall we break for questions now before I continue on?
Yeah, Joe, could you just expand a little bit on that K5, K6, K3 common cause failure?
Oh, right. So these are both the S3 and the K6 common cause. Okay. So if actually, I'm not quite done. I haven't set the gates the way they're supposed to be set. I haven't toggled the ors to the ands, so I'm going to do that in just a minute. But yeah, let's just expand upon that common cause failure. Going back to my schematic. So if S3 and the timer relay K6 both fail to open, two things happen. One is the arming circuit remains closed, so IV2 remains open. The other thing is that arming circuit, that opening is supposed to, of the arming circuit will also open the firing circuit, which also opens the timing circuit, which is responsible for closing IV3. So both IV2 and IV3 could remain open if those two components fail, right? So if, for instance, relay K5 on its own were to fail, that would cause IV3 to remain open, but so long as these two operate, IV2 will close and we're safe. So there's certain failures that can only affect one or the other valves, but these two components will affect both of them. So the way I modeled that in the fault tree was to copy and paste them, put them both in two different places. When I run the fault tree, when Reliability Workbench analyzes it, it sees these are the same components in both places. And it's the same components because I did that special adding an existing item. You can tell they're the same gates because they have the same ID. They're linked to each other, both in an editing standpoint. If I edit it in one place, it edits it in both places. From a computational standpoint, if it's failed in one place, it's failed in the other. Reliability Workbench knows how to take that into account when calculating cut sets. Okay, did that answer the question, Jeremy, do you think?
Yep, that sounds good. Thank you.
Okay. Any other questions?
None that need to be addressed right now.
Okay. Let me toggle the gates then to more accurately. Well, firstly, this shouldn't be an OR gate at the very top. It's an AND gate because both IV3 and IV2 must remain open. So long as I close one of those valves, there's no propellant to flow through the thrust chamber. So this needs to be an AND gate. I can't really change the gate type from the grid view. I can double click on the gate type, and what that's going to do is open the properties dialog, the gate properties. And I can just choose the gate type from here. Choose that because there's an AND gate. The other one that needs to be an AND gate, there's actually a couple more. The IV2 power supplied to IV2 after cutoff. Both the switch 3 and relay K6 must remain closed. Should either of those switches, should either the switch or the relay open, that's enough to break the circuit in relay K3, or excuse me, in the arming circuit. Same thing down here. Power supplied to K3 after cutoff. So I'm going to change that to an AND gate as well. Okay. So now that I have the correct fault tree, let's do a qualitative analysis. Oops, that's not what I wanted to click. I wanted to save it first. Then I wanted to set some project options. I want to do a qualitative analysis and look at the cut sets before I do a quantitative analysis. Qualitative analysis just looks for failure sequences. So I'll go to the project options, sets generation tab. What I need to do is I need to tell it to give me the complete cut sets. To expand the modularized sets is the option. I'm not going to get too much into modularization, but I'll just say by default, Reliability Workbench is engineered for speed and accuracy. So the options, the default project settings are towards those two things, speed and accuracy. Calculating full cut sets takes a little bit of time, so that option is turned off by default. But I'm going to turn it on. This kind of it's a little hidden option. It's one of the frequently asked questions: is how do we expand the cut sets? There's a particular option right here to expand the cut sets, and that's what I'm after. So select my options, click OK, click OK. Now when I run the analysis, I can go to the results summary and view the cut sets from my fault tree. Let's expand those sets. There we go. So this is a list of all the failure combinations which would cause the occurrence of the top gate. Thrust continues to be applied after cutoff. So if switch S3 is not depressed and relay K6 fails to open, or switch S3 is not depressed and the K6 timer fails to time out, or S3 operational failure fails to be depressed by the mechanism that's supposed to cause it to be activated, et cetera, et cetera. You can see each one of these represents a failure combination. So this is what I can look for. One of the useful things I can look for here is single point faults. I see there's no single point fault. There's no one component whose failure would cause the failure of the system. For each one of these, I can select it. So I can say this K3 and IV2. I can use the trace set. The program will highlight in red on the fault tree diagram the path from the top gate all the way down to the basic events that make up the cut set. So I can see how the failures are propagating their way up the tree. When done, I'll click the clear trace button. Okay. Now the next thing to consider, so I built this fault tree and I did this top-down approach, which is honestly the simplest way when you're first getting started, when you're looking for, when you feel a little bit overwhelmed by the system you're trying to model and you're trying to figure out how to get started. That top-down backwards approach is really the best way to go. However, it tends to produce large fault trees, sometimes overly complex in size fault trees. There's a way of simplifying the fault tree diagram by applying you can apply some logical rules and draw a fault tree diagram that provides the same failure logic, but in a more compact, perhaps easier to read and navigate diagram. So that's what we're going to do here. We're going to try and reduce this fault tree. The goal, again, is to produce those same cut sets, same combinations of events that produce the top event, but in a smaller package, so to speak. There's a couple of rules we can keep in mind when applying this simplification process. One rule is that linked groups of OR gates can be combined into a single OR gate. We see this often when we have a chain of component events. So the command fault of one component event is another component event. We'll often get these linked OR groups, linked groups of OR gates. Again, this is logically equivalent to the one on the right. So you have all the same basic events. They're all ORed underneath OR logic with each other, but this is a little bit smaller and more compact on the screen. Another rule we can follow is common failures underneath each branch of an AND gate can sometimes be reduced by bringing the common failure up and out and putting it next to the remaining events in the AND gate. So in this fault tree on the left, I have a common fault. It's a common event that appears underneath both branches of this AND gate. So I can move it up and out and put it next to, underneath an OR gate, the AND gate with the remaining independent faults of the AND gate. And these, again, are logically equivalent. Most users prefer drawing it on the right, but sometimes people will prefer the method on the left because it highlights the functional dependence, but it tends to produce a larger diagram. So this one is a little clearer, and this also makes it clear that it's a common failure, that you have a single point fault, so to speak, there. Okay, so let's do that in our reduced rocket fault tree, or rocket propulsion. S3 and K6 can be brought to the top of the tree because they are a common failure branch underneath both the IV2 and IV3 branches of the fault tree. And when we have those linked component events, we can put them all underneath a single OR gate. So let's take a look at what that will look like. Isn't quite done there. Alt tab back to our diagram. No, I'm not going to walk through this because it's a lot of tedious cutting and pasting. What I do to accomplish this is cut and paste, select this and cut it and move it around, move all these events around, create new gates. I think you sort of can figure that one out on your own. To move something, I can select it and use Control-X and Control-V to move it around. But basically what happens is these are common. So I'm going to create their own gates for these two items. Then everything else can sort of end up underneath its own separate branch of the tree. The component events for the IV3 and the component event for isolation valve IV2 will be under their own separate branch. Okay. So I'll just give you a sort of start this process off for you, and then I have a pre-done tree where that process has been finished. So I'm going to add a new gate. This will be where these, actually, you know what? Think about this. I can use my existing gates. What I'm going to do is just bring this one up to the top, cut it, and move it up to underneath the top gate, paste up there, and then I'm going to move everything else underneath a separate gate down here. Actually, what I'll do is I'll just create a new gate for my component events, cut it and paste it. I'm using my keyboard shortcuts Control-X and Control-V, Control-X and Control-V, Control-X and Control-V, like that. We'll delete this. I'll get the structure right. The descriptions won't match, though. So I'm just getting the structure. The final one would look something like that. I need to redo the descriptions on these gates here and add a description to this gate, but it ends up looking something like this. Okay, so let me switch over to my finished, completed one, finished and completed descriptions. There we go. So the way I renamed or relabeled the gates, the stressor is applied with propellant after cutoff if one of two things is true. The arming circuit remains closed, or the isolation valves remain open. The arming circuit would remain closed if the switch and the relay fail to open, and the isolation valves would remain open if any of those individual components, the IV2 remains closed, and that has to happen on the IV3 chain as well. IV3 has to remain closed, excuse me, has to remain opened, or the relays remain closed. Okay. Questions on that, Jeremy?
No, I'm just kind of answering questions privately. If anyone has any questions we don't get to, we'll respond to those after the meeting. So okay. All the questions have been answered for now. Okay.
So as you can see, the simplified tree is a little bit smaller than if I go back to the original tree I had. The original one was a little bit bigger, wasn't it? So this is easier. It's going to look nicer on the printout. It's going to be easier to navigate on the screen. And we can tell it's the same one. How do we know if it's the same tree? That's by looking at the cut sets. So if I rerun the analysis and check the cut sets, what I'll find is the same cut sets apply. So S3 off in K6, S3 in K6 timer. It's the same sets of cut sets, or the same 7 cut sets. So this is the thing with a fault tree, is you can draw a fault tree for, in nearly infinite ways. The way you can tell if two fault trees are equivalent to each other is by checking the cut sets. Okay, so that's the logic of the tree. Next thing we're going to want to do is quantify this tree, and in order for that, we'll need input values. What I've done for that, firstly, there's a couple disadvantages to that simplification process that I want to point out. One is it might be more difficult to understand how you arrived at the logic, because it no longer is a top-down deductive fault tree. So it might not be immediately obvious that you've accounted for all possibilities. It's not quite as deductive. Secondly, this is the easy one. Errors may be made in the construction process as you're cutting and pasting and moving things around. It's really easy to forget to toggle a gate the AND gate becomes an OR gate or vice versa. That can be easy to miss. So you have to be very careful and cautious when you're simplifying, when you're moving things around, to make sure you don't leave something out, delete an important piece of the tree, or anything like that. Okay. So let's quantify this tree now. In my Excel worksheet, where I had my components, I also have a list of failure models, or I pulled from a library, or from, I just have some data on the probability of any of these failures occurring. The failure to close for a valve, the failure to open for a relay, or failure to return to state when power is removed for the relay. For the K6 relay, the failure to time out, timer specifically. For the switch, the failure to open, the physical failure of the switch device, and the operational failure of the switching device. Just like I imported the basic events, I can also import failure models. It's an easy way to apply them. So I'm going to Control-C, put that on the clipboard, go back to my FaultTree, and I'm going to go through my import wizard again. This time importing from the clipboard to the failure models table. I'm saying the data on the clipboard is going to be the failure data, failure models. And again, I can use the auto match because I was careful about naming the columns and made sure that I use the same names that Reliability Workbench uses for its table. So Reliability Workbench says, oh, okay, it knows where I want that data to go. So, okay, you want the model type, that refers to the model type. I'll click Import, performs the import. Close that out. Now you'll see I have my new generic failure models that can be simply applied to the basic events by dragging and dropping them. To have it show up when I've applied a failure model is not always immediately obvious. I'm going to go to the View options and select the Show Failure Model IDs checkbox, and that will show me the when a failure model is attached by putting the ID underneath the basic event. So I have the failure to open when commanded, operational failure of the switch, the failure to return, failure of the switch to open, failure to time out, the failure of the valve to close, and the failure of the relays to open, etc., etc. Oh wait, that's an isolation valve. Okay, so I simply drag and drop my failure models into the FaultTree. And then the last thing that I might need to account for is common cause failures. There could be common cause failures of the relays or the isolation valves because they're the same type of component. So we could have some sort of lurking common cause events or common cause failure mode. Okay. Again, lastly, I have the common cause failure models. I only have 2 of them. So rather than importing them, I can easily just, almost as few clicks, just create it within the software. There's a common cause failure for the valves. Let me add that in. What was my beta factor? 10%. That seems kind of high. And then a common cause failure for the relays, which was 0.05. Okay. To apply the common cause failures, I'll just drag and drop those onto the associated components. The little beta flag that shows up next to the events. Okay. Also, again, I might want to show the common cause failure model IDs, so I can make sure I have the right CCF model applied. Because one thing I often make a mistake is dragging and dropping the wrong common cause failure model, which can sort of mess up your calculations a little bit. Okay. Now that I have the common cause failure models applied, and the failure models applied, I can perform the quantitative analysis. Let me just make sure my project options are set the way I want. I'm going to examine over a 10,000 hour lifetime. Let's turn on, no, I don't have any frequency data, so the MTTF won't be reliable. Okay. It's good, I'll just run the analysis. It calculates our top gate probability, this little grafter, as 2.5 times 10 to the -4th. So I could say there's a 0 to 5% chance that when we go to thrust, or when we run the thruster, that the thrust will continue even after it's been cut off. Okay, from there, we can go to the results summary to view additional, firstly, the quantification of the cut sets. From the results summary, we can look at the, there aren't too many other parameters calculated, so we don't have any frequency data. We can also look at the importance analysis. What's the most likely thing to cause it? Highest possible value of importance is the S3 op, the operational failure of the S3 open when commanded. Well, that would be, this is a pilot. It's basically the pilot's the weak link. He's the one who's most likely not to push the button. K6 time, the failure of the K6 time to timeout. So we find the weak links in the system, be the fossil Beasley importance, which events are most likely to contribute, and we can use that to recommend design changes or highlight further areas for analysis. How can we improve on that if we're trying to improve our gates, our system unavailability, improve the likelihood, lower the likelihood that the system will fail. Okay, I think we have just enough time for any remaining questions, Jeremy.
Yeah, let's, there's one interesting question that people might find of interest. Could you go over sequential failures really quick and show if you have one fault that needs to happen before a second fault happens, can you show how that's modeled?
Sure, okay, yeah, the sequential model, I have to think about, there might be a place in this where that could occur that I didn't think about. The way the sequential model works is for modeling failures that have to happen, or that can only happen in a specific sequence, meaning one component physically cannot fail until another component has failed. In certain FaultTree applications, you might hear this referred to as a dynamic gate. In Reliability Workbench, we call it we just call it a failure model. It's a sequential failure model used to handle that scenario. So I'm going to actually, instead of messing this up, I'm going to create a new, let's see, let me open up one of my other instances of Reliability Workbench that I have open. We'll just work from there. Just to show how it works, I'm going to create a new top gate. Let's say it has 3 events, and they can only fail in a specific order. Specific order. What I've used is the sequential model. So I'm going to create a new failure model and define a sequential model. What I enter is the failure rates. It can account for dormancy, so there could be a test interval as well. So our failure rate is 0.1 failures per unit time. Then there's this double and triple sequence flag, which tells me what sequence position can this item fail in. So you set the double sequence flag if it can fail, if it can be the second one to fail, and the triple sequence flag if it can be the third one to fail. So let me, if you open up the failure model, sequential model, if you open up the help file, you can find additional information. Actually, yeah, so the settings are 0 means it has to be, that it doesn't, excuse me, 0 means it can fail in that position. Negative means it can't fail at that position. Okay. So what I'm going to set is for, I have 3 events. So EV1, I'll set the triple sequence flag to 1, meaning it has to be the first failure. I'll create a new failure model for, so I don't need generic models, I can use local models. Again, entering some value here. For the triple sequence, I'll say 2, meaning it has to be the second to fail. And for the third one, again, sequential, I'll set the, again, same failure rate. Set the triple sequence flag to 3, means it has to be the third one to fail in sequence. The other thing is the sequence and group ID. You can have multiple groups of sequenced events within one project. So the group ID is how the program tells which other events it shares the failure sequence with. So you just, program doesn't care what you put there, just so long as it's a unique number. So you basically put the group number. This is group number 0, for instance. Okay. So I've said that this has to be the first one to fail, this has to be the second one, and that has to be the third one to fail in sequence. Okay. And there's certain cases, it comes up in aerospace. I didn't really consider it in the terms of this monopropellant engine, but maybe there are cases where that could occur. Okay. Any other questions on that, Jeremy?
Let's just do one more. So the question about common cause failures keeps coming up. I mean, in simple terms, it's gates named or events named as the exact same ID, right?
It's usually, yeah, for a common cause, oh, you mean the, like I did before where I copied and pasted the gates? Yeah, that was it. That was the explicit, what we call the explicit common cause failure model. Where here I have the little beta tags, those are what we call the implicit common cause failure model. But right, yeah, so the explicit model is where you copy and paste an item and have it appear multiple times on the project. It's called a repeat gate or a repeat event.
Okay. Yeah, if anybody else has any questions on common cause failures, please feel free to contact us after this meeting.
Yeah.
You have anything else you want to share on this, Joe?
You know, there's a number of other places we could go from here. I think this is good for an overview. The next thing to do might be to print out some graphs or reports. Jeremy, have we done a webinar on the report designer yet?
Yeah, there's actually a webinar on the blog that goes over the report designer.
Okay.
But that might be,
so that would be the next, yeah. That would be the next place to go from there.
Yeah. Well, let me share my screen really quick.
Okay. Okay, we can see your screen now, Jeremy.
Okay. So today we went through the FaultTree portion of the reliability workbench. We do have many modules in the reliability workbench if you're interested in things like prediction. The FaultTree includes Weibull, Markov, and event tree analysis, but we also have a reliability growth, RBD, and several other modules in there. One thing to note is that when the software is purchased, when you purchase maintenance, you do get technical support, which gives you access to people like Joe that can, although we're not consultants, so today's example was an example we took from a schematic. We're not an expert on that system. We can answer, if you can describe how a system works, we can usually answer questions on how to model that system. And for future, if anyone has any suggestions, recommendations, you have any questions on this webinar, please feel free to contact me. We will be setting up another one in a few weeks, and we'll be kind of researching topics. So if anybody has any ideas, let us know. Otherwise, thanks for attending today's webinar. Thanks for the presentation, Joe.
Oh, thank you. You're welcome.